Welcome to Study Loop.
Okay, so for this problem, you're given a PV diagram and you're asked what is the heat into or out of the system, the change in internal energy, and the work along each part. And then you're asked to kind of find the overall heat that went in and out, the overall work overall. Change in internal energy, and then the efficiency of the process. So this one is a kind of a review, I think, of the last section, except for kind of seen in the context of like heat engines. So the last questions are sort of the ones that are new. And so starting with part A, just getting our delta U's along each, and delta U, W, Q along each section. Let's just start from A to B. Isobaric part, the work done by the engine is P delta V. And then actually before I go work is P delta V. If you read off the graph, the pressure is, let me just pull up the graph so I have it and I can read off these numbers to you. Okay, so it's at 3 × 10⁵ pascals, and it's going from A to B, changing its volume by 0.3 meters cubed. And so if you plug that into your calculator, maybe you'll get what I got. Actually, you don't even need a calculator for this. It's just 0.3 times 3. So that's what I got. And then you want to get your delta U, and that's equal to NCV delta T. We can use our ideal gas law to get delta T. So for a constant pressure, you can just say it's P delta V over NR. If you plug that into here, then you get that CV over R. Nope, not equals. CV divided by R times P delta V is your delta U. And then if you use your delta V is 0.3, P is 3 × 10⁵, your CV is, I'll just write that on the side, CV equals 12.47, because they tell you it's a monatomic ideal gas. Okay, joules per mole Kelvin. Great. So if you plug in all those numbers, and R is 8.315 joule per mole Kelvin as well, you get that your delta U is 1.35 times 10 to the 5. These are both positive. You can see as you go from A to B, you're jumping to a higher isotherm, and you're also increasing the volume. So that means that the work done by the gas is positive. And then you can use this relationship. So this is going to come up and sort of be like the main, I don't know, I would say this is kind of a main equation. And equals Q minus the work done by the gas. And so you can get your Q from that. So you get Q is delta U plus the work done by the gas. And that is just the sum of these two things that we calculated. So, so then that gives you 2.25. I'm just doing that in my head. I guess that's right. Yeah, 2.25 joules. Great. So now we have from A to B. Let's do the same thing from B to C. So from B to C, one nice thing is that it's isochoric, so there's no work being done on the gas. So you could say the work's 0. It's only work if the volume changes. Again, your delta U is NCV delta T. And then instead of V changing, P is changing, and P and V kind of play the same role in the equation. Like they're just, they multiply each other. So if you kind of solve for delta T using PV as nRT, then you get CV divided by R times V delta P. And then delta P is 2 10 to the 5 pascals. Your CV is your 12.47. Your R is your 8.31. And then your V is 0.8 meters cubed. I'm just going to like double check my calculations on that. And let's see. 1247. Yeah. Divided by 8315. And let's see where I get my 2 point. Great. So then I get negative 2.39 times 10 to the 5 joules. So it's losing kinetic energy. Each particle loses kinetic energy. The temperature is decreasing. And you can see visually it jumps to a lower isotherm. So the sign makes sense. The fact that it's negative. And then that means the fact that work is 0 means that Q is also negative 2.39 times 10 to the 5 joules. And from C to A, let's see, the work done by the gas is the area under the curve, and it's negative because the gas is overall decreasing its volume. So it's like the area of this little trapezoid thing. Like if this is like your A, B, and C, it's the area under the curve, so it's this area. So I kind of broke it up into like a triangle and a rectangle. So first the area of the rectangle was 0.3 times 10 to the 5. I'm going to drop units or else it's going to get really messy. That was the pressure. Oh, excuse me. It should be 0.3 times 1 times 10 to the 5 because the pressure is, so this is your pressure, 1 10 to the 5, and there's your volume, 0.3 cubed. And then you want the area of this triangle, so 1/2 base times height, so 1/2 times 0.3, and then the height is 2 10 to the 5. Oh, my 5. When I put that into a calculator, I got minus 0.6 times 10 to the 5 joules. And you can get, now to get your delta U. So I originally calculated this like in the same way, like delta, I'll just do it this way. Well, okay. So your delta U is just CV over R, and then you just need to find the difference of PV. So you want PV at A, your final state, minus PV at B, your initial state. And again, this is just from using the ideal gas law. PV is nRT. And so if you use your 12.47, 8.31, you might get what I got, which is 1.05 times 10 to the 5 joules. And then if you want to finally compute your heat, again, use your delta U plus work by equals Q, and that's Q is equal to 0.45 times 10 to the 5. Oh, my 5s. All right, times 10 to the 5 joules, and that's keeping in mind that this 0.6 is negative. So overall, the heat was positive here. Great. And so we've done the heavy lifting. Now let's do the kind of final analysis, getting the total work. So the total work is just the signed sum of all the works, and I got, so the 0.9 plus 0.6, or excuse me, the 0.9 minus 0.6 all times 10 to the 5, which is 0.3 times 10 to the 5. It makes sense that it's positive because the area under the curve is positive. There's a bigger area. Geometrically, you can see the area is larger during the expansion than it was during the compression. And then Q is equal to, just summing up everything. 2.25 minus 2.39 minus plus 0.45, all 10 to the 5, is 0.31 times 10 to the 5. So overall, some heat had to get added to the system. Oops, I almost forgot my units on the work. And then delta U is 0 because delta U is a state-dependent thing. And since it's cyclic and it goes back to its original state, then delta U is 0 because the temperature is the same. So now to get the efficiency, so let's see, this was part B. Here's part C. So the efficiency is the work not divided by Q, only divided by the processes that produced positive Qs. So for that, for the work I did the just 0.3 10 to the 5, that's the total work. And then the Q hot, I only included the 2.25, which is the from A to B. So the heat added from A to B, which is 2.25 times 10 to the 5. I'll write this out. Plus the heat added from C to A, which is 0.45 times 10 to the 5. Oh, and these are both joules. So I'll just stick a little J's here. And if you add those together, if you compute this, maybe you'll get what I got, which is 11.1%.